this course on Electronics 1. This is AAA 231 being taught by me. This is my name. And this is fall 2021 session at Comstat University, Islamabad. Now, this course, as you can see, I mean, we will be dealing more often with electronic devices, and these electronic devices are inherently nonlinear to start with. Okay, so I mean, if you consider a basic p-n junction, it's uh, it's not a linear device like a resistor, so you cannot consider it as a linear circuit element. Okay, I mean the IV characteristics that you are going to see will be nonlinear. So, for example, if you have IV characteristic of a classical p-n junction diode, you might want to overcome some potential barrier before it starts conducting. That is the potential volts. Okay. Similarly, on the reverse side, the conduction is very small, so it's not a before the device breaks down, you have a very small conduction, so it's not a linear IV characteristic. So why such devices have nonlinear IV characteristics, and the mechanism by which the current is generated, how it differs from, let's say, conductors. It's different in semiconductors. So what we are going to do is, before we consider some circuits, and we start the formal talks on diodes or p-n junction devices, let's first look into the fundamental properties of semiconductor devices, why they behave as such. So, the course content, or the textbook to consult, I will. So you can consult Donald Niemann. Okay, this is the fourth edition of microelectronics circuit analysis and design. Fourth edition is available. You can get a PDF copy of it online. Okay, and it starts with the basic terminology and the properties associated with semiconductor devices, how the current is generated, and how the how the lattice structure of an intrinsic semiconductor looks like, and how you can increase the, for example, the concentration of charge carriers by process known as doping, and etc. These things are given in chapter 1 of this text. Okay, so I highly recommend that you get a copy of this textbook. Okay, for reference. Now, to start with, this is article 1.1 from your course text. It's on semiconductor materials and properties. Now, you see the most electronic devices which are fabricated by using semiconductor materials, along with conductor and insulators, are based on silicon. Okay, silicon is widely available. There are other advantages associated with silicon. For example, silicon is flexible. Okay, silicon has a better integration with front-end electronics. It's abundantly available. So we don't have just the elemental semiconductors like silicon or germanium. We have compound semiconductor as well. For example, you can have, for example, in optical devices, or where high switching applications, for high switching applications, you can have gallium arsenide. For example, you will see in transistor structures in MOSFETs, okay, with metal semiconductor field effect transistors, in radar applications or in gigahertz applications, for where the fast switching is required. You have the compound semiconductors as well. Okay. Similarly, you can have, for example, gallium phosphide based semiconductors. You can have aluminum phosphide, okay, aluminum arsenide, and indium phosphide. So, to gain a better understanding of the behavior of electronic devices in circuit, you must understand a few of the characteristics of semiconductor materials. Silicon is by far the most common semiconductor material and has been used for semiconductor devices and ICs. Now, other semiconductor materials are also used in specialized applications. I've already said. Um, for example, you can have this combination of group 3 and group 5 elements, which can be combined to form high switching or optical based electronic devices. Okay, like MOSFETs, or you have this in MOSFET structures as well, the elemental, the compound semiconductors. Okay, so it depends on the applications. Then to start with the basic structure of a pure semiconductor, let's have a look at an intrinsic semiconductor. Intrinsic semiconductor means you don't have any impurity added to it. It's a pure semiconductor. Okay, it's a pure single crystal. If you talk of a silicon, then it's a pure single crystal silicon. Okay, which has a tetrahedral form of a structure geometrically. And since silicon, silicon and germanium are group 4 elements. Okay, this is group 3 and group 5. This is group 4, which means you will have 4 electrons in the outermost valence shell, and they are loosely bounded to the nucleus, so they have more energy. So this defines the chemistry of such elements, where these valence electrons are going to contribute to the how they interact and how the chemical activity is based of these elements. So electrons in the outermost shells are called the valence electrons, and the chemical activity for material is purely determined by the number of such electrons. For example, in order to obtain a stable octet configuration, they need 4 more electrons with other 4 silicon atoms. Okay, so that's how the crystal is formed. So you see, electrons are distributed in various shells, and they are at different distances from the nucleus, and the electron energy increases as the shell radius increases. Well, what it means is that as you move away from nucleus, okay, so as you move away from, this is the nucleus, which is positively charged because of protons and neutrons, and then you have those shells, right? And as you move away from the positively charged in the atom, as you move away from the nucleus, the electrons are loosely bound, okay, are loosely bounded to the center nucleus, and they have more energy. Okay, so that is if, for example, if in a valence energy band. Uh, Valence energy band, first of all, they are responsible to create stable covalent bonds structures with the other silicon. They interact with other atoms. Okay, so they're going to have sharing over here. Okay, so for example, another silicon atom comes, and then this electron is going to be shared. For example, these circles are if these circles are belonging to this particular atom, and then these crosses are belong to the other neighboring valence electrons. So you see, this is how you're going to have bondings, right? So there will be another, for example, let's say a silicon atom, then there is a second silicon atom. So you will have this 4 silicon atoms to complete an octet structure, and this octet structure, you see, continues. Okay, I mean, there will be again some valence electrons left over, okay, which are going to bond with the next neighboring silicon atoms. Okay, so this picture might not look very great, but I mean, you can understand that what's going on. You need to have the sharing of electrons with the other silicon interacting atoms. Okay, uh, so you see, if you in this configuration, if you apply a certain electric field or you increase the temperature, the electrons are bounded. Okay, they're not going to break free. So semiconductors, unlike conductors, they don't have free charge carriers. All right, they can be generated thermally, yes, but it requires energy. Okay, the energy is required to make jump the electron in the valenced and when the valence energy band, from valence energy band to, let's say, conduction band, where the electrons can conduct. Okay, so that it's not as in the case of metals. Okay, metals don't have a very large difference between valence and conduction bands. Okay, the charge carriers are available. If they are insulated, then there is a large band gap, so you cannot break free the charge carriers over there. So insulators, they don't uh, favor conductivity much, right? But semiconductors, they fall in between. So over here you see elements. These are the elements in the periodic table, which you already know they are grouped according to the number of valence electrons. Okay. Now, as you see, this is group 3, which consists of boron, aluminum, gallium, indium. Okay, these are again these are very famous elements, which you will see later on. They are going to be used to dope single crystal silicon or a germanium to improve the concentration of charge carriers, which can contribute into the conduction process and generation of electric current in a semiconductor material. You see, in an intrinsic semiconductor, a pure semiconductor, is not a very good electrical conductor. You have to make it good by adding certain impurities, and these impurities are usually coming from either table 3, group 3 elements or group 5 elements like boron, aluminum, gallium, indium, or phosphorus, arsenic. For example, if a phosphorus is going to be introduced into the lattice of single crystal silicon, then this phosphorus is already having 5 valence electrons, and 1 valence electron is going to be contributed per atom of a phosphorus, and one mobile free charge electron is going to be present in the conduction band, which is going to improve the concentration of charge carrier and hence improve the conductivity of the material, right? Similarly, if you have group 3, then there is going to be an electron deficiency and there's going to be a hole. Although the atom or the impurity stays as it is, it's not going to, the atom is not going, the ion is not going to conduct. But the charge contribution is important to increase the conductivity of semiconductor material in extrinsic semiconductors. So this table 1.2 shows the portion of a periodic table in which more common semiconductors are found. Silicon and germanium are in group 4, and these are elemental semiconductors. In contrast, gallium arsenides are compound semiconductors. Now, you see in figure 1.1a, we have a silicon atom in a crystal matrix. Okay, so these lines which are emanating, they are showing you the electrons, the valence electrons. So each silicon atom, you take any silicon atom, it has 4 valence electrons around it. Okay, it's a group 4 element, therefore 4 valence electrons. And these dashed lines are they're showing the valence electrons of an atom. Now, as the silicon atoms come in close proximity to each other, the valence electrons, they interact to form a crystal. Okay, now this figure B is showing you the geometry. It's like a tetrahedron. For example, this is the center silicon atom. Okay, then you have 4 neighboring. Let's call this the first neighbor, and this is the second neighbor, third neighbor, and fourth neighbor. So each silicon is covalently bonded to 4 other neighbors to complete its octet structure. And the arrangement is in a tetrahedral fashion. Okay, the geometry is tetrahedral. Figure C is a 2-dimensional representation showing the covalent bonding. You see there are 2 lines, so it means the electrons has been shared. So for example, this center silicon atom has a stable octet structure. It has achieved 8 electrons in its outermost shell. And then the silicons on the outer edges, they still have this valence electron. Okay, so for example, this is not shared. So it has, so for example, other silicon atoms, they can come in, okay, and then they can start sharing with the neighboring silicon atoms. Okay, so you can have a very large single silicon crystal lattice structures. Okay, because valence electrons are always going to be present on the outer edges. Okay, so these are the outer edges, and you're going to have these valence electrons available, so all other silicon atoms can join in, and you can have a very large crystal structures of silicon. And the same goes for germanium and other group 4 elemental semiconductor elements. Okay, so the valence electrons are shared between atoms, forming what is called covalent bonds. Germanium, gallium arsenide, and many other semiconductor materials, they have same tetrahedral configuration. Even the compound semiconductors, they have this tetrahedral geometrical structures. Okay, now we are still talking of a pure semiconductor. You see, we don't have any impurity. We don't have any phosphorus or antimony added to the silicon structure. Okay, this is still a pure silicon crystal. Okay, right. Now, you see figure 1.1c that we have shown before has a representation of the lattice, which is formed by 5 silicon atoms, right? We have the center silicon, and then surrounding are 4 silicon atoms required to complete the stable structure of a silicon atom. And an important property of such a lattice is that the valence electrons are always available on the outer edge of the silicon crystal, so the additional atoms, they can be added to form a very large single crystal structures. Okay, so we have, more silicon can join in, more silicon atoms can join in to form very large tetrahedral lattice structures. Okay, so a 2-dimensional representation of a silicon crystal is shown in figure 1.2 over here. And you see where the temperature is 0 Kelvin, each line between the atom represents the valence electron. So you see it's a large crystal structure. We're having more silicon atoms which are covalently joined, bonded together with other four neighboring silicon atoms. But at such low temperatures, each electron is in its lowest possible energy state. It doesn't have energy to break free from the bond and start conducting. Okay, it doesn't have. You don't see any free charge carriers. So in this state, there is no conduction. There are no free carriers, and there is no conduction. So there are no free carriers, and there is no conduction. Okay, because the electrons in a valence energy state, valence energy band, they don't have energy to jump into the conduction band, break free from the covalent bonds, and start conducting. Okay, well, this energy has to be provided, and this can come through either applying electric field or a very strong electric field, or they can be thermally generated. Otherwise, there is no way. Okay, so each covalent bonding position is filled with electrons. You see two electrons on either side. Well, and planarly, they're all bonded. Okay, they cannot move. So if a small electric field is applied to this material, the electrons will not move, and because they'll still be bound to their individual atoms. Therefore, at T equal to 0 Kelvin, silicon is an insulator. There is no charge that flows through it. There's no free, because there are no free carriers. Okay. Now, what happens when silicon atoms they come together to form a crystal? Electrons, you see, the electrons they first of all they occupy particular allowed energy bands. In this case, in this configuration, the electrons are bonded in covalent bonds, and the energy state that they are having is the valence band where the electrons are bounded. Okay, they are, they have not yet jumped to conduction band. They are in valence band, and that's the lowest, um, call it energy band. Okay, so at T equal to 0, all the valence electrons they occupy the valence energy band. And if the temperature increases, the valence electron may gain thermal energy. So what happens over here? Look, you see in this figure 1.3, there's a breaking of a covalent bond. If you increase the temperature, then electron might get excited, and it jumps into the conduction band and create a positively charged empty state. Okay. So over here, you see if the electron jumps, then it leaves a positively empty charge. Okay, I mean it leaves its space. So there you're going to have a positive charge over here. Okay, because there's electron deficiency in this space, and this electron is generated, and it's generated from it gets enough energy. It breaks from the valence band and then goes into a conduction band, which where it starts conducting. Okay, although it is a thermally generated electron, one thing to note is that the crystal is still overall crystal is still neutral. Okay, I mean as more and more electrons are going to are going to be generated into the conduction band, or because since they are thermally generated, the electron deficiencies are equal to the electrons in the conduction band in the lattice, right? Which are going to contribute in the conduction. So these are thermally generated electrons, but the overall number of charged particles, positive and negative, they're equal. So the crystal is still as neutral. Okay. So any such electron may gain enough thermal energy to break the covalent bond and move away from its original position as schematically shown in figure 1.3. So in order to break the covalent bond, the valence electron must gain a minimum energy, e.g. called the band gap. Okay. And this band gap is a function of, you will see, the physics of semiconductor devices is such that the band gap has nothing to do with the temperature. Okay, it's fixed. It depends on the particular semiconductor material. For example, germanium has a different band gap. Okay, silicon has a different band gap. It's not dependent on temperature. So if the band gap is higher, then the material is more like as an insulator. Okay, you cannot provide energy to break free electrons easily from valence to the band gap. So the electrons that gain this minimum energy now exist in the conduction band and are said to be the free electrons. So these free electrons in the conduction band can move throughout the crystal, and the net flow of the electron in the conduction band generates a current.